Namaskaram. Welcome to a new session on multivariable calculus. In this session onwards, we will discuss integration on multivariable function. Okay. Before moving to double integration, we have to analyze the concept of single integration or definite integral like integral a to b f of x dx. I think all of you familiar with the evaluation of such integrals, and also we know that this integral represents area between y is equal to f of x and x-axis from a to b. Okay, this is the geometrical interpretation of this definite integral. Next, we are going to evaluate the same area using another way, like an infinite sum. Okay, for example, you consider a sum like this. That means, okay, our aim is to approximate or evaluating the area between this curve and x-axis from a to b. So first we subdivide this interval by choosing x0 as a, x1, x2, etc. xn is b. Okay, so choosing this much of points. Okay, next we are going to approximate this area. Suppose you consider a point x1 star. What is x1 star? X1 star is an arbitrary point from the first interval. Okay, x2 star is the arbitrary point from some arbitrary point from the second interval, like that. And one more thing, delta x1, delta x2, etc., delta xn. And what is the meaning of delta x1? Delta x1 means the length of this first subinterval, right? This length. That means x1 minus x0. And what is delta x2? Delta x2 is the length of the second subinterval. That means x2 minus x1. Clear? Like that. So we have delta x1, delta x2 up to delta xn and some arbitrary points from each interval. And x1 star is the first point, the point from the first interval, like that. Next, you think about f of x1 star into delta x1. What is this f of x1 star into delta x1? It is clear that delta x1 is this length. And what is f of x1 star? F of x1 star means value of the function at this point. So that is nothing, this height. So this height is f of x1, f of x1 star, right? This height is f of x1 star. Okay, so what about the product? We know that the area of a rectangular region with this width is a and height is b, then this area is ab. Okay, similar to here, what is f of x1 star? This is the height of a rectangular region and delta x1 is the width of this rectangular region. So this product is nothing, it is the area of a rectangular region like this. Okay, area of a rectangular region like this. Okay, then you think about the next one. Next one means you consider an arbitrary point from the second interval. Then this is the height. Then what is the product of this f of x1, f of x2 star into delta x2? This is an area of this rectangular region. Okay, continuing in this way, etc. The nth one, f of xn star into delta xn. So what about this sum? This sum is approximately the area between the curve and x-axis from a to b. That's why we use this formula. So we can approximate area using this finite sum. Sigma k equal to 1 to n f of xk star delta xk. When k equal to 1, this term. When k equal to 2, the second term, etc. When k equal to n, this term. You got the idea? So here we approximate the area using this sum. Okay, then how to improve this sum? Yes, it is clear that this sum contains some errors like this. Okay, and we can reduce this error if the size of the rectangle is the width of the rectangle is very small. Okay, it is equivalent to number of subintervals is very large. Clear? Length of each subinterval is very small means automatically number of subintervals is very large. So n is very large, automatically r is very small. So the extreme case is limit n tends to infinity, sigma k equal to 1 to n f of xk star delta xk. That is equal to our area between this curve and x-axis from a to b. Okay, so this is another interpretation of area using an infinite sum. Already we know that we can evaluate area using this definite integral. So combining these two, we have a new formula like this. This is the another interpretation of this integration, or we can interpret this infinite sum using this integration. Okay, using this idea, we can extend integration for multivariable function, or we can ready to we are ready to define double integration for a multivariable function. Okay, we will extend the same concept. Okay. Next, we are going to consider a function of two variable z equal f of xy. In the case of one variable function, we know that our domain is only a real line. That means x is varying only along a line. But in the case of two variable function, we know that our domain is a plane. So our points are moving along a plane. Okay. So here we consider the integration along a line segment from A to B. Instead of line segment A to B, here we have a region. Clear? And instead of a function y is equal to f of x, here we use z is equal to fxy. That's a surface. Okay. So the analogous concept is here area, here it is volume. So volume between a surface z is equal to fxy and xy plane bounded by a region. Okay. Region is analogous to the interval AB. Clear? Then how to evaluate this volume using the same concept? Okay, here we subdivide the interval as a small intervals. Instead of small intervals, here we are going to divide the region by small rectangles. Clear? Using lines parallel to the coordinate axis. Okay, that means lines parallel to y-axis and x-axis. Then you have so many rectangles in this region. Okay, and two rectangles, and exclude from the consideration all those subrectangles that contain any points outside of R. Okay, so we exclude this rectangle because some points are outside the region. We exclude these rectangles. Clear? So we consider only rectangles which is completely inside R. Clear? That is our first step. So we assume that there are n such rectangles. Okay, that means there are n such rectangles completely inside the region R. Okay, here it is, there are blue regions, blue rectangles. They are completely inside, and we assume that there are n such rectangles. And similar to one variable case, here we choose an arbitrary point from each interval. Here we choose arbitrary points from each subrectangle. Okay, and here what is delta x1? Delta x1 is the length of first subinterval. Here delta ak means area of the kth subrectangle. That means delta a1, that means area of the, let it be, this is first one, this is second one, third one, fourth one, like that. Then delta a1 is nothing, it is the area of the first rectangle. Okay, in general delta ak is the area of the kth rectangle. Clear? Okay, analogous to this means here we choose what is x1 star. X1 star is an arbitrary point from the first interval. So here we choose an arbitrary points from each rectangle. That means this red point, this is our first rectangle. So this is nothing, x1 star, y1 star. Clear? We choose this as our second rectangle. Then this is an arbitrary point. This is nothing, x2 star, y2 star. Clear? So similarly, we have n such points from each rectangle. And in general, xk star, yk star denote the arbitrary point from the kth rectangle. That's all. K is varying from 1 to n. Clear? Okay, our aim is to approximate the volume between the surface and this region. Okay, so now I think all of you clear what is our idea. So what is the volume corresponding to first rectangle? You take the area, that is delta a1, into height at this point. What is height at this point? F of x1 star y1 star, right? So f of x1 star y1 star into delta a1, this is the volume of this parallelepiped. Okay, then not this one, the parallelepiped at this point. Okay, next we consider f of x2 star y2 star into delta a2. So this is the volume corresponding to this area. Okay, so etc. we have up to n such parallelepipeds. So f of x1 star yn star delta an. Clear? So this is the approximate volume of this region. So we can write this volume approximately using this finite sum. So volume is approximately sigma k equal to 1 to 1 f of x k star y k star delta a k. Okay, this same sum. Similar to our one variable calculus, or in the case of area, we know that this sum has so many errors. Okay, and how to reduce the error? If the size of this subrectangle is very small, means area is automatically reduced. Okay, so or that is equivalent to number of sub rectangles is very large. Okay, so if you take as n tends to infinity, this sum is equal to the volume. Okay, that means error is very small and tending to 0. So we can approximate the volume, or we can evaluate the volume using the formula limit n tends to infinity sigma k equal to 1 to n f of x k star y k star delta a k, then infinite sum. Okay, so this infinite sum is exactly our volume. Clear? This is the extreme case. Okay, in one variable calculus, we know that this infinite sum is equal to integral a to b f of x dx. So what about this infinite sum? Here, instead of f of x, it is clear that our function is f of xy. And here, instead of delta xk, it is dx. So here, delta ak. So this becomes some dA. And what about here? It is clear that here the domain contains two variables. Domain depends two variables x and y. So that's why we use a double integration. Okay, double integration. In this case, the region is a to b. That's why we write like this, a to b. Here our region is something r. We denote the region by r. Okay, so double integral over r. So this is the notation of this infinite sum. Clear? So analogous to one variable calculus, we can denote this infinite sum using this notation. This is only a notation. So limit n tends to infinity sigma k equal to 1 to n f of x k star y k star delta a k is denoted by double integral over r f of xy dA. Now we can interpret this double integral as the volume between surface and a region. Okay, of course this double integration or this infinite sum has several other interpretations. This is the one basic interpretation, volume. For example, suppose we divide, this is our entire region. Okay, this is our entire region R. Suppose we divide the region as R1 and R2. Then by the concept of volume, we can interpret this notation, this double integration as a volume. So it is clear that the entire volume is equal to volume corresponding to R1 plus volume corresponding to R2. So this is the volume corresponding to R1, this is the volume corresponding to R2. So we can divide, or we can interpret double integral of R is equal to double integral of R1 plus double integral of R2. Okay, this is one important property of double integration. Okay, so there is a natural question, how to evaluate double integrations like this. So this is the actual formula of double integration, but it is clear that this is almost impossible. We have to divide the region as rectangles and choose an arbitrary point, and n tends to infinity. So there are infinitely many terms. This is almost impossible to evaluate. Okay, so in next session, we will see some easy formulas for evaluating these type of sums or these type of integrals. Okay, that means in next session we will see the evaluation of these type of double integrations using iterated single integrals. Okay, thank you.